am I live now? Okay, we are back. It's been a long time, I know. Let's just check the stream is working alright. Okay, we're back. It's been a long time, I know. Okay, it's not bad. Uh, so let's just send this. Alright. Okay. So we are back again to live streaming. I know it's been a long time. Um, Actually, I had a better background than this. I don't know how to get it back. Anyways, so we are back to live streaming. We are streaming in English now because someone just someone leave the comment on one of my videos before. He had a point though, so let's just go to my channel. YouTube.com. So it's been a long time. The last thing that I have streamed was like one and a half year ago. So in one of my videos, I don't remember exactly the video. I think it's maybe this one or this one. Let's see. Oh, I hate ads. I really hate ads. Okay. So that's enough. That's enough. Thank you. Thank you. So yeah, here's the comment I'm talking about. I mean, he got a point, right? He said, "Sir, please use English language." It's polite as well. Like, he started the comment with, "Sir, please use English language and discuss the different design and so on." So I think I had another comment about this, which someone says, if you are typing like an English title for the video, so the content should be in English. I think this was in another video, in another channel, not my channel, but it got the point though. Like, if your video's title is in English, like the viewer like expects uh, to watch like a video in English, right? Like most of the times. So I'm switching from Arabic to English, and I know like people who speak Arabic will understand the stream anyways. My English is not complicated, and this also will help me improve my English. So yeah, back to live streaming. I have a lot to say, um, and that's the beauty of live streaming. It's the place where you talk your mind, um, and like George Hodds once said, like his live streams, he was talking about himself, so I repeat what he's saying for me as well. Uh, those streams are for me, for you, which means like I get the benefit from those live streams before anyone gets the benefit, because like it's like it's the place where you have things in mind and you just like tell what's in your mind, and sometimes you explore new things that you are not interested to explore with yourself. um, I feel like I'm talking like Zlatan when he talks in English. Like he thinks twice before talking, because like it's not his first language, but it's normal. We will get uh, we will get with it. So let's see. I think I need to refactor my channel. Most of my videos are long. My latest video is 3 hours and a half. So I think I need to maybe cut some shorts from those videos. People like shorts. It's everywhere. It's on TikTok, on Instagram. I know like it's impossible for me to even download TikTok. But like the idea is that like shorts are like everywhere now, and also like we need to maybe do edited videos, because like most of my videos are not edited, because like I don't have time to edit my videos. I just stream raw videos, like and yeah, let's see how it goes. I know like this stream is in early morning. uh, we just got the sunrise here in Egypt, but let's just test things how it goes. It's been a long time, 1.5 years, didn't touch my YouTube channel. So let's get into our live stream. So today we are exploring something called XOR patterns. So I wrote this paper back in 2024. So this paper was about a choosing plain text attack on Ascon, and the attack is itself is not new. Like, it's about the idea of having the same key stream for two encryptions, for more than one encryption, and that's happened because the system, or like the function, doesn't change the nonce per encryption. So this is not new. It's been mentioned before in this paper, Vodny and Bizarre's paper. But like, my attack exploited a new path. It also required more queries than like the normal attack would take. But like, the thing is that I came into this patterns that I noticed during developing the online tool for Ascon, which is Play Ascon. I think it's still the only online tool for Ascon cipher on the internet. It's called Play Ascon. If you go to my GitHub blog, you will find it. So when I was developing this tool, and I have streamed the front end part of this tool on my YouTube when I was developing the front end of it, which is really fancy front end. I discovered like there is a pattern in the output of the XOR operation. So for example, if you have the same key, the same nonce, and you try to encrypt 0, 0, 0. So let's say 0 for now. This is raw, and this is in hex. So let's keep it raw. So the ciphertext will be 12 if you encrypt 1. And now, like, the difference between encryption of 0 and 1 is just like XORing 0 with a certain hex byte, and 1 is XORing 1 with a different with the same hex byte. So 0 and 1 are being XORed with the same hex byte. You notice this pattern, like 0 gives you 12 and 1 gives you 13, 2 gives you 10, back to 10. Okay, let's continue. 3 give you 11. Okay, 4 gives you 16. Okay, so the pattern is like 12, 13, then 10, 11, then 16. So it's like +1, +1 goes back two numbers back, 2 steps back, +1, +1, then goes 5 steps forward, or 4 steps forward, from 12 to 16. So anyways, like, it's something like dummy, but like I just gathered all the hexadecimal numbers in 1 byte, which is from 00 to FF, into groups, and I found that those groups have this like similar patterns. So for example, okay, starting from group 1. So we have 10 groups for like 256 numbers. You can spread them into 10 groups. So the first group, we have, for example, 0, we have 08, we have 10, we have 18, and so on in hexadecimal. So those have the same pattern of 1, 0, 0. So what's 1, 0, 0 stands for? 1 stands for something called SP. So it's been a long time, either like I didn't read this paper. Maybe we can like go through it again from the beginning, but let's just go with the patterns for now. So it says, yeah, so we have the sequential pattern, then the transition pattern, TP, then the transition frequency. So the sequential pattern is the pattern that we just mentioned, like from 0 to 1. So 0 gives us 12, 1 gives us 13. So that's plus 1. This is represented by 1. Okay? So yeah, 1 is the sequential pattern. And then like 0 and 1, and then if we continue to 2, you will hit like 2 steps back from 12 to 10. So we were on 13. So starting from 0, 12, 13, and then you go 2 steps back from when you have begun, like from 12 to 10. So this is the transition pattern. Okay, then you continue with the sequential pattern again. So from 10 you get 11, you expect to get 11. Before I like click the button, I'm expecting it's 11 because the sequential pattern is 1. And if you go to 4, you hit 16 now. So the thing is, like, the sequential pattern is let's just read it from the paper. It will be more organized. So this required me like a lot of thinking before writing this. So it's now easier for us to just read what I came up with. And this was written before like even ChatGPT came familiar, or at least like I didn't use AI to write this. So yeah, it will be clear to understand. So it says table 1 shows the classifications of the 10 groups based on their XOR patterns. An XOR pattern consists of 3 values: sequential pattern, SP, transition pattern, TP, and transition frequency, TF, represented as SP, TP, and TF. So a single pattern for each group is represented by those 3 variables: SP, TP, TF, sequential pattern, transition pattern, and then transition frequency. A sequential pattern is the change in the results of an XOR operation between a byte and 2 consecutive numbers, which can be either +1 or -1 all the time. Like the sequential pattern will be either +1 or -1. So let's just have a simple example. So we will have like we will write just a table. So we have we have X, okay, and then we have hex numbers, say, okay. So hex numbers is easy to fill, like let's say 0 0 0. Let's just hit tab and yeah, that's easier. Okay. So we have 0, we have 0 1. This is just counting, like 0 1 2, and X is like a hexadecimal number that we will pick from our groups and see its patterns. So let's just pick one number. For example, let's pick 0x18. So we will do an XOR of 0x18 with sequential numbers. So this will be an XOR between those. Okay. And let's continue. Let's continue for 10 numbers. 4, 5, 6, 7, 8, 9. This is just an example to understand the patterns I'm talking about. So for 0x18, we are expecting a sequential pattern of 1. That means, let's just do the XOR in Python. So our X is 0x18. Let's XOR it with 0 0. It will give us 24. Okay, that's better. Now we are expecting the next number to be like 25, because the sequential pattern starting from 0 0 is plus 1, so 25. Okay, so the next pattern is the transition pattern and then the transition frequency. The transition frequency tells you after how many sequential numbers the pattern will deviate. So the initial pattern is plus 1, but after a certain amount of numbers, the pattern will deviate. So this tells you the number, like how many numbers it needs to deviate from the pattern. Now for this group it says 0, so it will never deviate than 1. If we have this variable with another number than 0, for example here the transition frequency is 2, it tells you like the initial pattern, which is the sequential pattern, is -1. So if you started XORing with 0 0 and you get 12, for example, you expect the next the XOR operation with the next number will be 12 minus 1, which means 11. And then you look at the transition frequency after how many sequential numbers the pattern will deviate. So after 2 numbers, so I expect the next XOR pattern will deviate. How much it will deviate, this what the transition pattern tells you. It tells you it will deviate by plus 2. So it will be like from 12 to 11, then it will deviate plus 2, so it will go to 13 or something. Like, we will validate with some examples. So back to our 0x18, it tells us that it will never deviate. It will also add 1. So let's just try XORing, or let's just write a loop for this one. So for x in range 0x00 to 0x10, print x XORed with this will get us confused. So yeah, so our variable is x. Okay, let's just go with I. For I in range 0x00, 0x10, print x XORed with I. So each time it will XOR our 0x18 with I. I is like the range. It will be in range from 0 to 9 included. So let's see. So it's like 24, 25, 26, 27, 28, 29, and so on. And then it deviates by, interesting, it deviates by by minus 5, or no, not minus 5, it deviates by it's either like there's something wrong in the paper, or I didn't understand my work after this long time. So yeah, it deviates by 15. So the transition pattern should be minus 15, and the deviation appears after let's see, after 1, 2, 3, 4, 5, 6, 7, 8, after 8 numbers. So this should be written like this. This should be written like the sequential pattern is 1, and it deviates by 15 after 5 sequential numbers. Okay. Let's just make sure that we are doing the right thing here. Print print x and I, and x XORed with I. So yeah, 24 XORed with 0, with 1, 2, 3, 4, 5, 6. Okay. Okay. I think this is maybe this either a mistake in the paper, or because like I wrote code to prove this paper and it worked. I'm not sure. Okay, let's try another number. Let's go to the next group. It says let's take 51. So if we take x50 51 and we do the same loop for I in range 0 to 1 0, and this is from 0 to 15. Okay, it's been a long time. Print x and I, and then x XORed with I. Let's see. So it starts with 51, goes back to 50. That's the -1 sequential pattern. And then after two numbers, it deviates by 2. Deviates by 2, by -2. Okay, and then you go from 49 to 48, that's -1. And then it deviates. I think there is something wrong here. I'm not sure if I'm doing it right. Because now it deviates like after two numbers. Oh yeah, I remember. Okay. Because we didn't read the whole paper, we have something like a deviation from this deviation. Okay, yeah, we have another deviation, which is mentioned here. The first byte in each 16 consecutive numbers starting from 0 0 is called the starting point. The XOR result with a starting point deviate from the noticed patterns. Then patterns start to appear again. There are 16 starting points within the space of a byte from 0 0 to F0. For example, okay. So within the space of a byte. Okay, for example, the results of XORing 0C with 10 will not follow any of the previously mentioned patterns. The result of XORing with the starting point should be obtained first. Then the result of XOR with the next 15 numbers will follow the extracted patterns again and can be predicted without applying XOR operations. So it says that after 16 numbers the pattern will deviate. But the thing is that it deviated before 16, so I'm not sure our example is correct. 51, 50, okay. Then it goes 55, 54. Goes back by 1, 53, from 50, okay, 55, oh, so, okay, 54, 50, 55, 54, 53, 52, should we print this in hexa? Okay. For range print. So this is -1, minus. Oh, okay. I did something really stupid. So yeah, I understand now. Hopefully my paper is not wrong. Like, is not wrong. Like, hopefully I am doing the wrong thing here. So yeah, those are hexadecimal numbers, but like we wrote it in Python in decimal. So we picked here, for example, 51. It should be 0x51, which is not 51 actually, which is 81. But let's stick with hexa. Okay, so again, let's validate this again. So yeah, let's pick 51 again and see. 51. Let's, for I in range 00 to 010, print hex XOR or XORing X with I. Okay, X with I. Okay. So now it's 51, goes back to 50. That's the sequential pattern -1. Then after two numbers, it deviates by +2, which goes from the first number that we began with to 2 steps forward, so from 51 to 53. Then the sequential pattern appears again, which is -1, from 53 to 52. Then after two numbers we have the transition pattern, which is again positive 2. So add 2 to 53, it becomes 55. The sequential pattern appears again, 55 to 54. Add two numbers. Now we have moved 2 steps. After moving 2 steps, the transition pattern will appear, which is you get the first number you started with, which is 55. You add 2 on it, so it becomes 57. Start again with the sequential pattern, which is -1, from 57 to 56, and then add 2 to 57, becomes 59, and so on. Yeah, now it's clear. Okay, and after 16 numbers, you will hit something called the starting point. So after 16 numbers, you will get a result that deviates from all those 3 patterns. Okay, this is only the if this operation, like, we are treating XOR as like a natural phenomenon or something. Like you are imagine yourself, you are just watching like electrons, for example, moving in some random moves, and then in some random directions, and then you notice like you can extract some pattern from there, but the pattern holds for a certain amount of time, then it deviates, then it goes back to the same pattern, and then it deviates within the same amount of time that it deviated before. So that's the thing. Like, it's dummy thing here, because like we know how to do XORing. Like, you can just do it with paper and pen. You can write like the binary of 51, hex at 51, and then you XOR it with like 0 0 0 1 0 0 0, whatever. You can like say like 1 XOR 0 is 1, 0 XOR 1 is 1, and so on. It's easy to do it in paper and pen. It's easy to do it in Python. But the thing is that I treated XOR as something not predictable. You are watching something like you are watching, like you are sending inputs and watching the output, and you don't know the operation is XOR, but you are eventually extracting patterns from those results. That's the abstract idea. Okay, so yeah, after 16 numbers it will deviate, so we can do the same loop with longer range. So yeah, for I in range 0 to, let's say, F0, print XOR hex of XORing X with I, and then let's go back to the paper, which is thankfully correct. I was wrong at the beginning. So it says here there are 16 starting points within the space of a byte. Okay, so it says the first byte in each 16 consecutive numbers starting from 0 is called the starting point. So it says like, yeah, so you can notice the pattern. Like this means like you cannot expect the starting point. For example, like you don't know that the system at the back end XORs your input with 50 with hexa with 0x51 here. So here, because we wrote the code, we know that we are XORing x. X is just like x is 0. Let's just print x. X is 0x51. So what we are doing here is that we are XORing 0x51 with our input. So our input is just consecutive numbers from 0 to F0 in hexa. So imagine like you don't know what the system is doing in the backend. You don't know what's the algorithm it's implemented there, or like let's just imagine it like in biology, for example, like there is something happening inside the cell that you don't see, but you provide some inputs and you notice the outputs and you try to extract patterns from the output. So the first you cannot expect the first output. You can never expect, like it's like if the range of the output is like if the probability or the range, or if the range of the possible numbers in the output is in range from 0 to 255, the probability you can expect the output is 1 out of 255. You cannot like expect more than that. Like you cannot be sure if it's like totally random, if it's like 100% random, and we assume that because you don't know anything about the system, like, okay, so the first output can never be guessed, okay, so that's why I called it the starting point. So at the beginning we threw an input of 0x00, and the first output that came out is 0x51. Like the maximum probability of guessing 0x51 is 1 on 255 if the output range is just from 0 to 255. So this is not, you cannot guess it, okay? So it's 51. And then what I did is that I pretended I don't know like what's the system doing. I'm just extracting patterns from the output. So from 51 to 50, that's -1, and then it goes like it adds two numbers at it adds two numbers on the first output. So it adds 2 to 51, gives you 53. Okay, so now after two outputs, which is the transition frequency, it deviated by 2 steps forward. So from 51 to 53. And now we repeat the sequential pattern from 53, as we had like -1 before from 55 to 50. We will also have a step back again from 53 to 52. And then after two outputs, which is the transition frequency, we will get the transition pattern, which is deviating by +2, adding 2 to the first input after previous or after latest deviation. So from 53, it deviates by +2 to 55, and so on. And then after 16 numbers, like the number, I think the number like after 16, maybe the number 7, the 17th number will be a new starting point, a new thing that you cannot expect, you cannot guess. So let's count. That's 1, 2, 3, 4, 5, 6, 7. Those are, you can guess those from the tables I extracted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Those are all expected. Like after the starting point, you can guess the rest. But like after 16 steps, it deviated from 5E to 41. That's the point you cannot expect. But the thing is that this starting point, which is a complete deviation from the pattern, also gets repeated after 16 steps. So the randomness is still expected at somehow. So you expect after 16 steps that another randomness will appear. So from 41 to 40, it goes back to the patterns that we know. So from 41 to 40 is the -1 sequential pattern. And then after two numbers, which is the transition frequency, we hit the transition pattern, which is you take the first output from latest deviation and add 2 on it, you get 43. 42, -1, then 45, and so on. And let's count 16 numbers and we will hit a new randomness. So as you can see, it's 4, 4, 4, 4. You will hit a new number after 16 steps. So 41, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's just make it 15, 16, and then you cannot expect the next number. You cannot guess it. Let's just see. 71. Ignoring that the operation is just XORing. Ignoring that, like you are just watching something like a biological cell or something. So yeah, that applies for the rest of the groups. We just tested 51, and I tested all those groups on the patterns I extracted with Python, I promise. And I have like an implementation of like exploiting this to attack ASCON in a nonce misuse environment, and it's on GitHub. If you go to github.com motarek, I think it was M24 paper. Because it was published in 20 24. So that's the Python implementation. It's a little bit of a messy code, but it works. I'm not sure if I'm going to into this code today because I'm not in my best condition today. Like, I didn't sleep for a long time, but like I didn't want to wait for the perfect conditions to start streaming again, so I just start streaming. So yeah, that's the basic idea behind it. So I used those patterns to blindly expect the XOR, the output of the XOR operation, and like to perform like a chosen plain text attack on ASCON. So this attack requires more queries than the normal attack would take. So I mentioned that here. Like, the results show that this attack requires 160 queries to the encryption oracle for each ciphertext block decryption. This is more than number of required queries in one of the previous works that proposed a CPA attack that requires only one query for each ciphertext block. So my attack requires 160x of number of the queries that previously mentioned attacks require. But the thing is, like what I did is that instead of taking like this is like this is the objective of the attack, for example, okay, and instead of taking like a straight line to achieve like the attack with one query per ciphertext block, I took like longer way, but with a different approach, exploiting XOR patterns, and it took me like 160 queries per ciphertext block, which is still applicable in a polynomial time, like in an applicable time. Like, it's still practical, okay. But yeah, that's really a general idea behind it. I will not go through the whole paper. I will not go through the whole the details of the code. Maybe this will be in the next live stream. But let's just talk with AI today about those patterns. So the thing is that I'm not interested to go through how I exploited those patterns in this attack, but I'm interested in other applications, new applications. Can we can those patterns be useful in other applications? So I mentioned like some of this in the, I think in the conclusion of the paper, or maybe in this section. I mentioned something about key exchange schemes. Okay, schemes, yeah. So I said additionally, okay, starts from here. Let's just start from the beginning of this section. So it says XOR patterns. When performing bitwise XOR operations between a single hexadecimal byte and consecutive numbers 0, 1, 2, etc., a noticeable pattern appears in the results. Hence, the 256 possible byte values from 00 to FF can be classified into 10 groups, as shown in Table 1. Those are the groups. 10 groups. Each group exhibits a consistent pattern in the results of the XOR operation. These patterns can be exploited to predict the outcomes of XOR operation. Additionally, this is the part we are interested in. Two parties can use these patterns to generate different numbers with the same XOR pattern without knowing each other's number. This capability could be useful in developing new key exchange and zero-knowledge proof schemes. Further exploration of how XOR patterns can be utilized in these cryptographic applications is left for future work. So that's the part this whole stream is about. And I'm open to just explore this like on a YouTube live stream, because I really don't care. So let's just try this. Let's ask like ChatGPT, let's ask Gemini if they have like ideas about it. So let's just upload the paper to those let's start with ChatGPT. I prefer Gemini at the beginning. I will just upload the paper. The paper is on IEEE, by the way. Oh, I cannot upload on Gemini free. I think I can upload on ChatGPT. So yeah, the paper, you can just look up the paper, CPA decryption attack, ASCON. So here's the paper. Let's see if we can upload documents here. Are we still streaming? Like, is the stream working? Oh, nice, it's working. So yeah, let's continue. Yeah, we can upload photos. That's weird. I think we will just copy and paste the whole paper. Okay, let's just give it like longest context that we can provide. So yeah, we'll learn or let's just say read this paper and be ready for questions I will ask. Okay, so let's say paper title. I think it will say like you reached the context limit. I think we should chunk this. We should divide this into chunks. So yeah, maybe we can just okay. So let's just do this. I will upload the paper in chunks, different messages, so that let's just pretend that this is for like for his benefit, instead of just that we don't have the primary account. So yeah, so that you can grasp each section individually. So this is the title, and we can start with the introduction and abstract. Let's continue the related work, and then the contribution. Okay, let's just give it related work, and then the contribution. Actually, like, I need to isolate the context of using those patterns in Ascon, in attacking Ascon. So I need to talk about the patterns itself. Let's just try, like, let's just open a new thread, and I have noticed patterns in the XOR operation. Let's just not mention the paper. XOR operation. Okay. Let's just mention that what are those XOR patterns about? provide this table. Okay, let's open it in Word. To make it fit in one column. To take a clean screenshot. This doc doesn't include the table. How about this one? Nope. Shouldn't be this the final draft I wrote? No, it's not. Let's see. Oh, nice. Here we go. So that was the poster I used to discuss the paper in the conference. I just want to take a screenshot for the XOR patterns table. Can we just do a clean zoom out? Where is view? Okay. Okay. That's enough. Here we go. Okay. So we mentioned what are those patterns about. Now we need to tell it the call of action. So do you agree okay. How can we say it? Should we say validate, or we can say, we can either say validate those applications like using XOR patterns in like I mentioned 3 applications here. Obviously predicting the output of the XOR operation, and then key exchange or zero knowledge proof. Zero knowledge proof, where it is. Yeah. So we can either say validate those application and we can start with this. So validate the usability of the usability of those patterns within the mentioned applications. Okay. We can also copy our prompt so we can maybe use it with other models. So it says the patterns you have identified are real in the sense that they arise from the algebraic structure of XOR. The key question is whether they provide new computational leverage or new cryptographic capability. Those are very different claims. The patterns are mathematically expected. XOR is not a random operation. It's addition over the vector space, the Galois field 2 to the power of 8. For any byte A, f of x equals A XOR x is simply a permutation of the numbers from 0 to 255. When you evaluate A XOR 0, A XOR 1, A XOR 2, and so on, the jumps between consecutive outputs are completely determined by the carry structure of ordinary integer addition. For example, A XORed with x plus 1 minus A XORed with x depends only on which low bits of x flip when incremented. Let's see. A XORed with x plus 1 So A XORed with x plus 1 means like XORing with the next consecutive number minus A XORed with the previous number. Depends only on which low bits of x flip when incremented. Okay? That's exactly why you observe periodic behaviors of length 2, 4, 8, 16, and so on, which correspond to carries propagating through successive bits. So the patterns are genuine, but they are manifestations of binary arithmetic rather than hidden properties of XOR. Why exactly 10 groups? Looking at your table from 1 to 6, etc., notice something important. Every group is determined entirely by the lower 4 bits of the byte. For example, 0C, 2C, and so on all belong to the same group. That means the upper nibble has absolutely no influence. This is expected because carries generated while incrementing consecutive numbers only depend on the low bits until a multiple of 16 is reached. That explains why we are hitting the starting points. So your starting points are exactly where the carry reaches bit 4. Okay. This is not an empirical coincidence. It follows directly from binary addition. Okay, can these patterns predict XOR? Yes, but only in the same sense that knowing 1, 0, 0, etc. allows you to predict the next binary number. But only in the same sense that knowing... Yeah, I understand. You are replacing XOR computation with an equivalent recurrence relation. Instead of computing A XOR X, you compute previous value plus 1 plus 1 plus negative 4 plus 1 and so on. Interesting. According to the pattern, that is according to the pattern. You compute those according to the pattern. So I'm just skipping the XOR and following those patterns. This is a different algorithm for producing exactly the same permutation. It does not reveal information that XOR itself hides. That's completely true. Computational advantage. Suppose we already know A XOR 16, then your recurrence predict A XOR 17, A XOR 18, and etc. without another XOR. This is true. However, modern CPUs, I'm impressed by the length of the response. To be honest, yeah, it's amazing. This is true. However, modern CPUs compute XOR in one cycle. Following your recurrence requires branch logic, additions, pattern lookup, and so on. I understand that I'm making things more complex, which is generally slower than XOR itself. So this is mathematically interesting, but unlikely to be computationally advantageous. Okay. Can two parties generate different numbers with the same XOR pattern? Yes. Many numbers share the same lower nibble. For example, 0C, 2C, 5C, and so on. So what it's saying about sharing the same lower nibble is so a nibble is if we are representing a byte with 8 bits, a nibble is just 4 zeros, and lower nibble and higher nibble depends on if you are in a least significant, if you are using if you are using big Indian or little Indian. So it depends. So let's say lower nibble in little Indian. So in a little Indian system, the lower nibble are the 4 least significant bits. We need an example. We can just print those. So yeah, what is the default Indian of Python terminal? I think it's little Indian. Oh, it's usually little Indian. It depends on the architecture though. Yeah, so we are on Intel, so yeah, it's little endian. So it says here like those numbers share the same lower nibble. So if we print binary 0C and then 2C 5C 5C EC. So the thing is that if we fill like we can do a small padding function like function. Okay, this is Python def pad. So we are padding a number, and then we are printing okay, if length of x is less than 8 while length of x is less than 8, we will add 0. Oh, we can just say x equals 0 plus x, 0 plus x, yeah. And then we will return x. So that's our padding function. We can say pad this, for example. Oh, we can just say pad this, but skip 0b. Yeah, so I did it wrong here. Oh, we can just, oh, okay, so I'm sorry, it's like 2 starts from 2. Yeah, so that's the padding. Okay, so now, yeah, if we just printed binary of those numbers 0x 0c 2c 5c EC. So what it says here is that those numbers share the same lower nibble. So it appears the lower nibble it's talking about is the 4 numbers on the rightmost, which should be the, like, this is little endian, so little endian means the least significant bit is on the right, like on the rightmost. So does little endian mean oh, it means exactly the opposite. Oh yeah, the least significant number. This keeps me confusing, like the little bit endian and big endian. Okay, give examples. And like, by the way, like, they changed Ascon. Nest changed the Indianness of Ascon from I remember, if I remember correct, from Big Indian to Little Indian. So I needed to go back and update my code. So yeah, so play Ascon is now implementing the latest updates of Ascon. So yeah, if we encrypt, for example, hello, it will give you this value, and I have an old implementation of play Ascon. Like, if we use the same key and the same nonce, it will give us a different result. That's because like the Indianness was changed, so that's a different result. Anyways, so yeah, if we want to, okay, so it says 258 in hexadecimal is 0102. Okay. Uh, 01 is the most significant byte. Okay. 02 is the least significant byte. Okay. In Big Indian, how it looks in memory, in Big Indian from left to right. So it begins with 01 to 02. In Little Indian, it's the opposite. So Python. Okay, so this is Big Indian. This is not Little Indian. So yeah, this is Big Indian. And the least significant bits are on the rightmost. Anyways, so yeah, it says like many numbers share the same lower nibble. For example, those numbers. So the same lower nibble. So lower, like I think lower indicates like the lowest, the least significant bits, which are on the rightmost. So yeah, 1100, 1100, 1100. So the lower nibble is the four rightmost numbers. All belong to the same group. They therefore generate identical transition behavior. This is because A XOR X depends on every bit. But your pattern only captures the behavior introduced by the lowest 4 bits. So many bytes collapse into the same pattern. This is expected. Can this be used for key exchange? This is where the proposal breaks down. A key exchange requires a hard mathematical problem. Examples include discrete logarithm factoring, lattice problems, isogenes, and so on. Your patterns provide no hard problem. Suppose Alice announces pattern 1 minus 4 4. Immediately the attacker knows the key must be one of those. There are only 16 possibilities. For an 8-bit example, this leaks 4 bits immediately. For larger bit strings, the same phenomenon generalizes. The pattern reveals structural information while leaving no computational difficulty. An attacker can enumerate all compatible values. There is no one-way function. But the thing is that you can say like, okay, so there are only 16 numbers to predict within this pattern, because this is only 1 byte, but the key will not consist of only 1 byte. So yeah, if you have like 32 bytes key, each byte with a different pattern, so that's the difference here. Yeah, we can keep talking about this. Okay, can this support zero knowledge proofs? I have no idea about this, to be honest. Like, can this be possible in zero knowledge proof? Again, not by itself. Zero knowledge protocols require completeness, soundness, zero knowledge. The crucial ingredient is a hard witness relation. Your pattern is not hard to compute. Anyone can determine SPTPTF for the bytes. How about like a string of bytes, not only 1 byte? Likewise, anyone can enumerate all bytes sharing the same pattern. Okay, therefore knowledge of the pattern does not constitute a computationally hard secret. Without a hard relation, a zero knowledge proof cannot derive security from it. Anyways, I'm not expecting a lot from those patterns to contribute in crypto applications. This is like nearly possible, nearly impossible. But let's just keep going, and maybe we can like have like a hint for an application in a whole different field. Information theoretic viewpoint. Your classification maps 256 bytes into 10 classes. That means the pattern contains at most log to 10, log 10 base 2. Okay, so that's the bits of information. So that's the entropy of those 10 classes. The original byte contains 8 bits. Okay, so the pattern discards almost 5 bits of entropy. A cryptographic primitive cannot recover those lost bits. That's interesting. Can this be used in compression? Where this work is valuable, I think the strongest contribution is not cryptography but characterizing XOR permutations. Where this work is valuable, I think the strongest contribution is not cryptography but characterizing XOR permutations. Specifically, your work identifies equivalence classes of bytes under the finite difference sequence. Oh, so delta X is A XORed with the like the next number minus the previous one. I'm not sure. Oh, okay. This holds for delta X. Okay, this is an interesting combinatorial object. What the heck is this? Okay.
Combinatorial
objects. In the area of mathematics, primarily concerned with counting both as a means and as an end to obtaining results, and certain properties of finite structures. It's closely related to many other areas of mathematics and has many applications ranging from logic to statistical physics. Okay. I'm sure those patterns can be useful in somewhere, but I need collaboration with someone in pure mathematics, or in maybe in physics, or maybe in like in pure computer science. I think this could be useful anywhere. So yeah, possible directions include deriving the thing classes analytically rather than empirically. What is the difference between analytical and empirical? Interesting. Analytical relies on logic, deduction, and mathematical reasoning, while empirical relies on real-world observation, experimentation, and data collection. So it says we can derive, rather than empirically. That's what I'm talking about. Like, that's the initial analogy I used about like observing an electron or a cell, and you extract some patterns. And the thing is that, like, when we have the deviation, the random deviation on those starting points, this is something similar to what is called the pattern of randomness. Like, there is a graph called maybe the randomness graph. And this graph. So I want to give credit to my brother who discussed this with me before. Like, there is a graph for randomness. Like, randomness itself appears in noticeable patterns. So this is the thing, like, the starting point is random, but you can expect when the starting points will appear. After 16 numbers, you will hit a starting point, you will hit a randomness. That's the beautiful thing about XOR patterns. Introduction to random graphs. Oh, that seems interesting. I respect Carnegie Mellon University. Models and relationships. Supercritical phase. Okay. Degrees of sparse random graphs. So we have sparse random graphs and dense random graphs. Let's see the difference between those. Okay. Sparse random graphs with many triangles. In graph theory, a sparse random graph of a dense random graph typically refers to extracting or observing subgraph or a spanner from a dense space graph. The goal is to retain as much of the original graph's spectral connectivity or metric properties as possible while using a significantly smaller fraction of edges. Anyways, let's continue. Okay. What about combinatorial? Discrete finite structures such as graphs, permutations, combinations, and set partitions. Okay. So it says deriving the 10 classes analytically rather than empirically. So again, analytically versus empirically. Analytical approach derives conclusion through logic, mathematical modeling, empirical real-world observation. So it says that we can derive 10 classes analytically rather than empirically. Okay. If we assume that we don't know that the operation behind under the hood is XOR, so yeah, we can derive the results analytically rather than empirically, proving why there are exactly 10 classes. Okay, extending the classification to 16, 32, and 64-bit words. Interesting. That's a good suggestion, to be honest, because those 10 classes are only for the range from 0 to 255, which is a byte long word. How about 16? How about 32? It's like an architecture. Okay, expressing the patterns using gray codes or Wallace Hammer transforms. Okay. What is gray codes? Specialized binary numerical system where two successive values differ by exactly 1 bit. By ensuring that one digit changes state during any increment, it prevents transitional errors, often called glitches. That really looks like what I did. What? Oh. What is it used for though? Also known as reflected binary code, also known as reflected binary or gray code after Frank Gray, is an ordinary. Who's Frank Gray? 1930. Okay. As an ordering of the binary numeral system, as an ordering of the binary numerical system such that two successive values differ in only 1 bit. Okay. Seems like the sequential pattern that I was talking about. But this is just incrementing numbers. Okay, the sequential pattern I mentioned is by XORing numbers. That's the difference. For example, the representation of the decimal value 1 in binary would normally be 001, and 2 would be 010. In gray code, these values are represented as following. Okay. It's not like 2 is not represented by 010, it's represented by 011. That way, incrementing a value from 1 to 2 requires only 1 bit to change instead of 2. Oh, that's a different thing. That's a different thing. So it's just pushing this binary 1 to the left one step, and then adds another one, and I think 3 would be like 0111. So yeah, okay. No, like 3 is 10, still 10. But how is 3 is 10? So yeah, okay, so gray code is a different representation. It's not like a binary representation, okay? So it's a different representation. It's an ordering of the binary, like it's not the normal ordering we are using. So we normally write 2 as 010, but here it writes 2 as 11, and so on. 4 is written as 110, and so on. So for example, 4 here normally is 100. In gray code it's 110. So yeah, as you can see, like bits are pushed to the left. So this is useful in some way. I think this is useful in some way. I don't know where. It says it's widely used to prevent spurious output from electromechanical switches, and to facilitate error correction in digital communications such as digital terrestrial television and some cable TV systems and so on. Okay. Okay. The binary reflected gray code represents the underlying scheme of the classical Chinese rings puzzle. Okay. What is expressing the patterns using gray codes? Or so it says like we can express the pattern using gray codes. I don't think this will add something, but yeah, it introduced us to new concepts anyways. So this Walsh-Hadamard transform is orthogonal non-sinusoidal mathematical operation that decomposes a signal into a set of rectangular basis functions, Walsh functions, taking values of positive 1 or negative 1. It offers high computational efficiency. So can we have like a visual for this? Yeah. Okay. I think those things are useful in network channels and so on. Okay. Relating the classes to carry propagation in binary addition. Studying the finite difference operator on XOR permutations. Studying the finite difference operator on XOR permutations. This would constitute a solid mathematical contribution. Okay. Your observed patterns are valid and reflect genuine structural properties of XOR under sequential inputs. They can indeed be used to reconstruct future XOR outputs from a known starting value. And a recurrence, although this is generally not faster than performing XOR directly, obviously. However, the leap to cryptographic application is not supported by current evidence. That's true. The pattern classes reveal only a small amount of information about the byte, are easy to compute, and do not create a computationally hard problem. Consequently, they do not by themselves provide a foundation for secure key exchange. Okay, or zero-knowledge proof. The most promising direction is to formalize these observations mathematically. A rigorous proof explaining why exactly 10 equivalence classes arise, characterizing them in terms of the low-order bits and carry propagation, and extending the analysis to large word sizes would make the work substantially stronger. If a cryptographic application is still desired, it would need to introduce an independent hard problem. The XOR patterns themselves are best viewed as a descriptive property of XOR permutations rather than a source of... Okay, I'm not expecting too much about cryptographic applications. The XOR patterns are a naive thing, but maybe this could be contributing to information theory or to pure computer science or something. So, okay, can this help in compressing data? Can XOR patterns? It's just a naive question. Possibly, but not the way suggested by the XOR patterns group. Okay, short answer: do not reduce the information content of arbitrary data so they cannot be the why patterns alone cannot compress data. Lossless compression is fundamentally about reducing redundancy. Suppose a byte is uniformly random. Its XOR pattern class 1 of your 10 groups contains only about 3.3 bits of information, but the original byte contains 8 bits. Many bytes share the same pattern. Knowing the pattern leaves 16 possible bytes, therefore the pattern cannot replace. XOR is already used in compression. Interestingly, XOR itself is widely used in modern compressors. For example, delta encoding. Instead of storing those, you can store differences. Okay. For binary data, XOR is often used instead of subtraction. A XOR A, B XOR C, and so on. If neighboring values are similar, many XOR differences become small and powerful. This compresses well. For binary data, XOR is often used instead of subtraction. A XOR B, B XOR C, C XOR D. if neighboring values are similar, many XOR differences become small. Let's compress as well. I didn't understand this one. Floating point compression. Facebook's Gorilla database stores previous value XOR current value. Interesting. Because successive floating point values differ in only a few bits. Many XOR results contain long runs of zeros. These runs compress extremely well. Okay. Could your XOR patterns help? This is where your work becomes interesting rather than storing bytes. Suppose you store pattern. If the data naturally contains long sequences whose XOR behavior follows one of your 10 classes, you might be able to include the sequence more compactly. For example, instead of this, you might include start pattern group 8 length 16. Okay. This resembles run length encoding or direction encoding. The benefit depends entirely on whether the data contains such repeated structures. That's a very narrow case. Well, it worth researching. So yeah, those things are open. Like anyone who would like to work on this, like it's open for everyone. I'm sharing ideas because yeah, I don't care too much about like if someone can work on this better than me, like I will be happy. Okay, that's the thing. The goal is to reach something new. Whoever reaches this thing, because at the end of the day, like I started those patterns, mentioning those patterns. I don't think those patterns were mentioned anywhere before. So like this is like enough for me for now. Like if I can explore more, it's good. If someone else can build on this, it really doesn't make a big difference for me. So yeah, a more promising research direction. Your classification may be useful for modeling XOR transformed data. And also imagine this, imagine 10 different people started from this with either the same topic, like for example, using those patterns in compression, or in different topics, which is better, like in different PhDs, for example. I don't want to be to expect much from this. Maybe it will be just like a graduation project or a master's thesis or something. But yeah, if this opens like research paths, that's incredible. That will be incredible for me. Yeah. So yeah, I will make shorts from this live stream. Maybe it will reach more people, and I will post on LinkedIn as well, and maybe some people can benefit from this. Okay, a more promising research direction. Your classification may be useful for modeling XOR transformed data. Suppose you XOR adjacent bytes in a file. My right eye wants to sleep so bad. So. Okay. Suppose you XOR adjacent bytes in a file. So D of I, or xi XORed with xi minus 1. Okay, so D is the result of XORing two adjacent bytes. Then classify every byte into your 10 groups. In natural files, text, images, executables, sensors, logs produce highly skewed distributions among those groups. That seems interesting. In natural files, produce highly skewed distributions among those groups, then include the pattern IDs, include only the remaining information needed to reconstruct the exact bytes, compress the pattern stream using entropy coding. If the pattern distribution is highly non-uniform, this could provide a modest gain. How to validate the idea? A good experiment would compare the entropy before and after applying your pattern classification. Sure. Take several datasets. Plain text, JSON, source code, images, audio, executables, random byte. For each, compute the original entropy, compute XOR differences between adjacent bytes, map each XOR byte to one of your 10 pattern classes, measure the entropy of the pattern IDs, measure the entropy of the residual information needed to recover the exact byte, compare the total compressed size with standard methods such as Huffman coding, etc. If your representation lowers the total entropy of structure, then the pattern has practical value as a this will be awesome if this applies. Overall assessment, the 10 XOR pattern classes are not themselves a compression method because they discard information and cannot uniquely represent arbitrary bytes. However, they could be useful as a feature extraction or pre-processing step if they expose statistical regularities in certain types of data. The key question is empirical. Do real-world datasets exhibit a biased distribution of these pattern classes or long runs of the same class? If they do, then your classification could contribute to a specialized compression scheme, even if it's unlikely to outperform general. Okay. How about steganography? Okay. Can we use could XOR patterns be useful in steganography? Okay. No, thank you. It's not responding anymore. Okay. Okay. It's still thinking. Hopefully it doesn't break. Okay. Yes, this is actually a more plausible application than key exchange or zero knowledge proofs. The question is whether your XOR pattern classification okay, we got the full response. The question is whether your XOR pattern classification offers any advantage over existing steganographic techniques. I think there are several research directions worth investigating. Pattern preserving embedding. One goal of steganography is to modify data without introducing detectable statistical artifacts. Suppose a cover file has XOR pattern sequence where G1 to G to G10 are your pattern groups. Okay, suppose a cover file has XOR pattern sequence G5, G5, G6, G5, G8, G and so on. Okay, by the way, you can represent any bytes, any random or non-random bytes with this representation. By, like, you say, like, the first byte the first byte, I forgot the word. The first byte I forgot the word. I want to say the first byte is from group 1, but with another word. The first byte. I really want to sleep. Belongs to, yeah. The first byte belongs to group 5 or class 5. Let's call it a group. And the second byte also belongs to group 5. The second byte belongs to group 6, and so on. You can represent any string of bytes with this representation. Okay, where G, okay, instead of embedding, okay, so you can, instead of embedding data by flipping arbitrary bits, which changes local statistics, you could constrain modifications so that each modified byte remains in the same XOR pattern group. Interesting. So 0C could be replaced by 4C, and both are in the same group, which is also in group 5. If the decoder knows the mapping rule, the choice among equivalent bytes could encode hidden information. Advantages: preserves local XOR pattern statistics, potentially reduces detectability by static analysis. Disadvantages: only 16 equivalent bytes exist per group. Many substitutions may noticeably alter the original data. Okay. Encoding data by choosing equivalent bytes. Since each pattern group contains multiple bytes, you have roughly 16 choices. Not all groups though, like you have groups which you only have like 1, 2, 3, 4, 5, 6, 7, 8 numbers in it, but like it just says the average number, like 16 choices for each occurrence. Those choices could encode 4 bits of hidden information if changing the byte is otherwise acceptable. This resembles existing techniques like syndrome coding or matrix embedding, where multiple equivalent representations are used to carry payload bits. Okay. I'm also thinking about do you remember the penguin issue of ECB mode of operation? The thing is, like, if you want to hide an image, or if you want to hide an information inside an image, so for example, if the original form of the image is this colored penguin, if you don't mind that after decoding, like, if you take this penguin and you obfuscate it using steganography, and you don't mind that the intended recipient, after decoding the obfuscated image, will get something like this, because it's a penguin at the end of the day. It's still a penguin. Like, the recipient will receive the right message anyways. If you don't mind that the penguin color will change, but at least it keeps being a penguin, maybe that relates to the patterns I'm talking about, or any kind of patterns. Okay, so you don't like mind about, you don't care about changing the colors of bitmaps. So yeah, anyway, so it says here, this resembles existing techniques like, okay, syndrome coding, etc. The challenge is finding context where replacing one byte with another in the same group does not corrupt the underlying file. Okay, XOR pattern domain instead of bit domain. XOR pattern domain instead of bit domain. Most steganographic algorithms operate on least significant bits, transform coefficients, prediction, residuals. Your idea suggests embedding in a new domain. Original byte, XOR transform, pattern classification, and then embed message by controlled pattern changes. This is conceptually interesting. The question becomes, can pattern changes be made while remaining statistically indistinguishable from natural XOR pattern distributions? That is a measurable research question. Steganographic key, a sender and receiver could agree on which pattern groups may be modified. How equivalent bytes represent payload bits. How equivalent bytes represent payload bits. How equivalent bytes represent payload bits. Which starting points are skipped. The secret key determines the mapping. An attacker observing only bytes sees ordinary XOR statistics. Whether this improves security over existing key embedding methods would require evaluation. Resistance to statistical detection. So again, those are like ideas of how we can like of exploring applying XOR patterns in steganography. So here it says resistance to statistical detection. This is probably the strongest research direction. Most statistic analysis detects changes in histograms, neighboring differences, noise models, prediction errors. You could investigate whether preserving XOR pattern you could investigate whether preserving XOR pattern frequencies also preserves higher order statistics. For example, compute pattern histograms for natural images. Embed data while preserving the histogram. Train a static analyzer. Compare detection accuracy against LSP replacement and matrix embedding. If detection rates decrease, your patterns have practical value. But again, like where are, oh, okay. So it says compute pattern histograms for natural images. Okay, adapting embedding. Suppose certain pattern groups occur frequently in natural images. Adapting embedding. Suppose certain pattern groups occur frequently in natural images. Instead of embedding uniformly, embed only in group 5 and group 6. That's interesting. Or whichever groups exhibit the highest natural variability. That's interesting. This is similar to modern adaptive steganography, which hides data in noisy regions. Yeah. Limitations. Several issues would need to be addressed. File integrity, changing 0C to AC preserves the pattern, but it changes 4 bits. Again, this goes back to the penguin issue. If you accept that the color of the penguin will change, but it will still be a penguin. If you accept this, so yeah, this will apply. For compressed images, executables, encrypted files, or text, this usually corrupts the data. Okay. Therefore, the method cannot generally operate directly on arbitrary bytes. Capacity. Pattern preservation greatly restricts allowable modifications. Embedding capacity may therefore be lower than conventional techniques. Okay. Existing methods already exploit equivalence. Modern steganography already uses ideas such as syndrome coding, wet paper codes, matrix embedding, syndrome trellis codes, which also seek multiple equivalent modifications while minimizing distortion. Your contribution would need to demonstrate the XOR pattern equivalence offers lower distortion or better resistance to detection than these established approaches. A concrete research plan. The idea is testable. Implement your 10-group classifier. Compute XOR pattern distributions for natural images. Design an embedding algorithm that preserves pattern frequencies. Compare against those strategies. Measure those metrics, and then if you have an improvement, your work is valid. Meaningful contribution. Among applications you have suggested so far, steganography is the most promising, unlike cryptography. Unlike cryptography and compression. Okay. Okay. Let's just talk our minds with AI. Like the analogy came to my mind. Okay. Let's say, let's not just tell the story of our lives. Let's just say there is an analogy, or okay, let's say analogy. Let's say validate this analogy. Having random starting points, then predictable XOR patterns is like having random starting points, then predictable XOR patterns with the starting points such that the occurrence of starting points, the occurrences of starting points are predictable. Every 16 numbers, consecutive numbers. Is like predicting when randomness will occur. Is like predicting when randomness will occur which also could relate to the randomness graph. What was it called again? Randomness graph. Degree. Oh, okay. It's random graph. Okay. Like the random could relate to the random graph. Predictable random graph. I think it has a name, a special name. Predictable graph of a random set. Okay. Do we have an image of this? Actual and predicted values. Okay. Randomness graph. Let's just call it randomness graph for now. Okay, interesting. But as stated, it overreaches mathematically. There are two separate ideas: predicting where structural discontinuous occur, predicting randomness itself. Your XOR observations support the first, but not the second. What your observations actually show for a fixed byte, consider f of x is a XORed with x, from 0 to 255. You observe that within each block of 16 consecutive inputs, the output falls at deterministic recurrence, your XOR pattern. At multiple of 16, the recurrence resets, requiring a new starting value. This is completely explained by binary arithmetic. Incrementing a number propagates carries through the lower 4 bits and every I see something here. This is explained by binary arithmetic, but that's because we know those patterns are an output of an XOR operation. But what if we don't know that the operation is XOR? We cannot easily prove it arithmetically. We cannot easily explain it arithmetically. So apply this on randomness that comes from other systems that includes more complex operations inside of it. Okay, and every 16 increments carry reaches the 5th bit, changing the recurrence. Okay, so what you have is a piecewise deterministic process. Starting point, random independent initial value, deterministic evolution for 15 steps, next starting point, and so on. Deterministic evolution. This is a bad characterization, where the analogy becomes incorrect. You wrote predicting when randomness will occur. The starting points are not random events. They occur exactly at 0, 16, 32, and so on. Their locations are completely deterministic. The only thing that might be viewed as new information is the XOR value at that starting point, not the occurrence of the starting point itself. The only thing that might be viewed as new information is the XOR value at that starting point, not the occurrence of the starting point itself. A better wording would be: the recurrence identifies the deterministic regions of the XOR sequence and the fixed locations where a new initial condition is required. This is much stronger mathematical statement. Again, the recurrence identifies the deterministic regions of the XOR sequence and the fixed locations where a new initial condition is required. Does this relate to a randomness graph? It depends on what you mean by randomness graph. If you mean a graph showing where entropy is introduced versus where values are determined by recurrence, then yes, there is conceptual connection. Your sequence could be viewed as independent value, deterministic, and then independent value, and so on. This resembles systems studied in finite automata, dynamical systems, Markov models with periodic resets, piecewise deterministic processes. In those settings, one often distinguishes between points where new information enters the system and intervals where the evolution is completely determined. Information theoretic interpretation. This is perhaps the strongest way to express your idea. Instead of saying randomness occurs every 16 numbers, every block of 16 inputs requires one independent initial condition. The remaining 15 outputs are determined by the recurrence. This is a statement about degrees of freedom, not randomness. For example, input block. If the XOR value at 16 is known, your recurrence determines 17, 18 until 31. No additional independent information is required within that block. Relation to entropy. If the recurrence is exact, then the entropy of the sequence satisfies approximately entropy of the block. Okay, because every other value is a deterministic function of the starting value. This is an information theoretic observation, although it doesn't reduce the entropy of the original XOR mapping. It merely reflects that you have changed the representation. A refined analogy. Instead of comparing it to predicting when randomness occurs, the XOR sequence behaves like a deterministic dynamical system with periodic boundary conditions. Every 16 inputs introduce a new initial condition, after which the next 15 outputs evolve according to a fixed recurrence. Thus, the locations requiring new information are completely predictable, while the values at those locations determine the subsequent evolution. This framing is mathematically accurate and avoids implying that. Okay, your intuition that the sequence alternates between points requiring new information and switches evolution is a useful way to think about the phenomenon. The analogy becomes misleading only when it suggests that the occurrence of randomness is being predicted. He really didn't like this phrase, like he commented on this phrase a lot. In your XOR construction, the reset locations are not random at all. They are fixed by the binary carry structure. The more rigorous interpretation is that you have identified the predictable locations where new initial conditions are needed, which is statement about structure and information flow rather than about randomness itself. Okay. Here is another topic for maybe a thesis, like anyone can follow. Anyone can work on mathematical framework for periodic information refresh, not as a model of true randomness. Here are some examples. Okay. Gene regulation. Okay, so that's the model. Um, so yeah, genes regulation, external signal, then gene activation, predictable transcription, protein production, another external signal. So the external signal is the starting point, the starting unpredictable point, and then the upcoming the is the unexpected step, but the upcoming steps are predictable. So that's the same thing: starting point, predictable XOR evolution, and then a starting point, and so on. The analogy is that an external biological signal establishes a new initial condition, after which the cellular machinery follows deterministic uh, biochemical rules until the next regulatory event. This is conceptual. This is conceptual. This is conceptual analogy rather than a direct mathematical equivalence. Another example: cell division. Cells pass through ordered phases, G1S, G2M. Most of the cycle is highly regulated and predictable. Only certain checkpoints introduce new decisions based on DNA damage, nutrients, and signaling. Again, checkpoint, deterministic progression, checkpoint, and so on. Structure resembles your recurrence plus reset model. Evolution. Evolution is often described as mutation selection, population changes, mutation selection. Mutations introduce new genetic information. Natural selection then deterministically changes. Okay, this is very similar in spirit to new information, deterministic information, new information. Neural activity spike, predictable voltage decay, and so on. Chaos and dynamical systems, initial condition, deterministic equations, complex behavior. Your XOR recurrence is much simpler but follows the same general principle. One initial state determines an entire subsequent trajectory. Where the analogy breaks down, nature generally does not have fixed resets every 16 steps. Your XOR reset periods come from binary arithmetic. Biological system, that's the thing I'm talking about. it comes from binary arithmetic. Maybe nature have something else, something more complex than binary arithmetic. Okay. This is a philosophical thing. Like, is there really a pure randomness, true pure randomness, or we just don't know the underlying function? Because if you think about it, if you have like, so pseudo-random number generators works like this. You have a function that does bunch of steps, and it accepts a seed as an input, does bunch of steps, then returns an output that looks random. And each time you change the seed, even by 1 bit, the output looks random based on previous outputs. So does nature operate like this? Like, it accepts an input, which is a seed, and then does bunch of calculations, and then outputs a value that looks random for us, and then the next time the seed changes, and so the output changes as well. The thing is, we don't know this function, so it appears random for us. So we consider, if we assume nature works like this, like pseudo-random number generators, and there is no true random numbers or true random generators. If we assume that, then we just consider random generators that we don't know their underlying function. We consider those as true random generators. But if someone knows the underlying function, it becomes a pseudo number generator for him, at least. Or if we know that this guy knows the underlying function, we will still call it a pseudo-random number generator, because we know this is not truly truly randomly generated. Anyways, it's a trivial topic. I think this topic has been discussed before, but yeah, we are just talking in our minds here. Biological systems usually have stochastic timing, feedback, variable cycle lengths, multiple but as you can see, like, we discovered some natural operations that are done in a predictable sequence, just by having proper observations and many experiments. So now we know, for example, the life cycle of how genes are regulated. So genes are not expressed randomly all the time. A cell often behaves like this: external signal, gene activation, predictable transcription, protein production, and so on. Okay. maybe this appeared random at the first time for the observer, but then after repeating the same experiment conditions, we got the same results, so we labeled this as predictable. Okay, again, here it says, okay, okay. Neurons. After neurons, so it says many natural systems are deterministic but appear random because they are highly sensitive to initial conditions. That's the thing. For example, weather, fluid turbulence. What does this mean? Fluid motion. Okay. Planetary resonances. Okay. These systems have initial condition deterministic equations, complex behavior. Your XOR recurrence is much simpler but follows the same general principle. One initial state determines an entire subsequent trajectory. Where the analogy breaks down, nature generally does not have fixed resets every 16 steps. Your XOR reset period comes from binary arithmetic. Biological systems usually have stochastic timing, feedback, variable cycle lengths, multiple interacting processes, so the periodicity is specific to XOR, not to biology. A better abstraction, instead of saying biology has XOR patterns, it's more accurate to say many biological systems can be viewed as alternating between information generating events and deterministic evolution. That abstraction is shared. Okay, this is where the analogy holds. Information theory connection, your strongest interdisciplinary connection is probably information theory. Many natural systems can be modeled as information enters, system evolves deterministically, information enters, system evolves, and so on. Examples, I'm wondering why it didn't mention pseudo-random number generators here. DNA mutations, sensory input, immune responses, ecological disturbances, earthquakes, and so on. Your XOR observations describe an idealized version where information enters at known intervals. Evolution between intervals is exactly predictable. Nature usually replaces known intervals with random or state-dependent intervals. A possible generalization, your work may be more valuable if generalized beyond XOR. XOR has 10 patterns. Consider developing a broader concept. Periodic information refresh systems. Okay. Systems in which a small amount of new information periodically determines a longer interval of predictable behavior. This framework could apply to digital circuits, error correcting codes, communication protocols, biological regulatory networks. I need to record this conversation. I will just copy paste the answers after the stream. It's really valuable. and maybe I will share it with you as well, so it becomes easier for you to just look up topics and maybe extract ideas from this. So this framework could apply to digital circuits, error correcting codes, communication protocols, biological regulatory networks, hybrid dynamical systems, predictive compression. The mathematics would no longer depend specifically on XOR, but on identifying systems that alternate between innovation, which is new information, and deterministic propagation. Overall assessment: there is no evidence that your XOR patterns directly explain biological randomness or natural randomness. However, they do illustrate a more general principle. A system can require occasional new information. A system can require occasional new information while remaining predictable between those events. That principle appears across biology, neuroscience, control systems, and dynamical systems. If you present your work as a model of information flow and periodic state updates rather than as a model of randomness itself, the analogy becomes much stronger and aligns with established concepts in information theory and computer science. Okay, but isn't this model introduced before? I see. Okay. Yes, the general idea has been introduced before, although probably not the exact form you are describing. The novelty depends on what you claim. There are several existing frameworks that separate new information from deterministic evolution. Dynamic systems: a system starts from an initial condition. Deterministic equations evolve the state. If the system is perturbed, a new initial condition is established. This is one of the oldest mathematical frameworks in physics. Markov processes: the future depends only on the current state. Randomness enters through state transitions. Okay, between transitions, evolution is determined by the model. That seems like what we are talking about. is Markov process is a type of random stochastic process where the probability of a system future state depends slowly on its current state. It operates on the memoryless principle. What happens next ignores the past and relies only on the present condition, and it's mathematically expressed as well, which is cool. Hmm. So we have types of Markov processes, and then we have Markov chains. These processes have a discrete state space, a countable number of possible states, like categories or integers. Thing that strongly relates to what we were talking about. Discrete time Markov chain. The system transitions from one state to another at specific, separate time steps. Okay. Discrete time Markov chain. So who's Markov? I'm curious. Like, when did he put this? Maybe I just reached the same thing, but like, how many years later? Yeah, it's maybe it's in the beginning of 20th century. So yeah, we are like 100 years ahead. Okay, so this was mentioned 100 years before. Continuous time Markov chain. The system can change its states at any random moment in time. Nice. So can we consider the pattern of starting of random starting points appearing in fixed periods as a discrete time Markov chain? This argument is becoming more interesting, not in its current form. DTMC has a very specific mathematical definition, and your XOR recurrence does not satisfy. However, it's closely related, and with slight modification, it can be represented as a Markov chain. So a DTMC is a set of states, discrete time steps, transition probabilities. Okay, your XOR process, suppose the state is this. You observed a starting point, predictable recurrence, and then a starting point. The recurrence is completely deterministic. For example, state 0 to state 1 to state 2 with probability 1 at every step. That is technically a deterministic Markov chain if you include enough information in the state. The problem with random starting points, you describe the starting point as random, but in XOR. It keeps saying this. I'm not trying to say that the occurrence of starting points is random. I'm saying like starting points value is random, looks random. That's what I mean, but it keeps misunderstanding this. Okay. Let's just mention this to AI. Okay, so what I mean by random starting points is that the value of the starting point itself appears random. But I am not referring to the randomness of starting point occurrence. I admit that starting point occurrence is deterministic every 15 numbers, but the value of it appears random, different from previous patterns, sequential patterns. How can I describe it clearer than this? Thanks for clarification. Okay, that's much stronger. Thank you. Okay. Okay. It's not random. It appears to be random because, again, we know it's an. Okay, let's just say this. Okay. I said starting point value appears to be random, but in fact it's not. But we know, we are sure that it's not random because we know that the underlying operation is XOR. But if we don't know the underlying operation, operation that produces those patterns, including starting points in this case starting points will really appear to be random. Okay, let's read this theorem here. For every byte A, interesting, it just wrote a theorem. How amazing is this? For every byte A, the sequence A XOR X can be partitioned into blocks of length 16. Within each block, all values are generated. Within each block, all values are generated by deterministic recurrence from the block's initial value. The recurrence alone does not determine the initial value of the next block. Knowledge of the hidden parameter A is required. That's a solid theory. Oh, okay. That is such a solid theory. Notice this says nothing about randomness. It's entirely deterministic, yet it captures exactly what you have observed. That exactly represents the whole XOR patterns thing. Okay, good work. Okay. Okay. So again, what did it say after this beautiful theory? We need to ask it about Markov chains again, but let's just see what did it say after the theorem. Where is the theorem? Where did it go? Okay. 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 And then here comes the theorem. I think this is the key insight. Earlier I was interpreting, okay. Each starting value acts like an anchor or seed for the next 15 outputs. Here we go. Once the anchor is known, the remainder of the block is predictable. That is a much cleaner interpretation. Okay, that's just a conclusion. So then we said that we say it's not random because we know the underlying function. How about if we don't know the underlying function? Now your statement becomes more precise and it touches a real concept in information theory and cryptography. I'm sure it will mention the pseudo-random generators now. Yeah, it mentioned it, yeah. What you are describing is essentially a deterministic process can produce outputs that are indistinguishable from random unless the generating rule or the state is known. The idea is not only valid, it's foundational in modern cryptography. Yes, appears random is a real and formal concept. What you are calling starting points appear random, if we don't know the XOR, is formally called computational or observational indistinguishability. A sequence is random looking if no efficient observer can predict the next value better than chance. Better than, as I said, like if you have like a set of finite numbers that you can choose from 0 to 100, for example, no way you can gain more probability than 1 on 100. Okay, there is nothing better than a chance, like, okay, so yeah, or cannot distinguish it from a tree random sequence when even though the process is fully deterministic. Okay, your XOR case, what is actually happening, you have f of x a XOR a XOR x, and you focus on starting points. A XOR 16 k. If an observer does not know A, only sees the sequence of the starting values, then they see something like this. That's cool. I didn't thought about this before. How about if we increase the word size from just a byte to 32 bytes, and then gather all the starting points. So each byte has 16 starting points. If we have 32 bytes, we will have 512 random, or let's say pseudo-random starting points. Okay, pseudo-random starting points. So now, like, the system we are talking about is like, if you want to make it abstract, so we have like known periods that gives us predictable outputs, but the initializer of those periods is pseudo-random, which means like appears random. So as long as you make your sequence larger, you will have more random points. Okay, but the thing is, okay, I'm not sure if those starting points will still look random when we increase the word size. we can quickly try this, but like I think yeah it will. Let's just assume it will appear random. So the thing is that again, if you have 32-byte word, you will have 512 starting points, 512 pseudo-random points. Okay, and this just appears from XORing with consecutive XORing the same byte or the same word with consecutive numbers. Right? So even though internally it is like this, so yes, from the observer's perspective, this looks like an unpredictable sequence. But crucially, it is not random, it is solely random under hidden state. The key idea, apparent randomness equals hidden structure. What you discovered is a classic pattern, deterministic system plus hidden parameter equals apparent randomness. This is exactly the same structure as cryptographic pseudorandom number generators. Example: ES encounter mode, Cha-Cha-20 stream cipher. They produce output that looks random if you don't know the state. To someone without the key, output looks random but are fully deterministic. Your XOR system is a toy version of this structure, except the key is just a single byte A, so it's very weak. Linear congruential generators, the same thing. Chaotic systems, okay. Important correction, you said we are sure it's not random because we know XOR. Yes, but more precisely, it's not random because it's computable, it's invertible, it's fully determined by a hidden state, but it still can appear random because observer lacks hidden parameter. Mapping hides structure in a simple algebraic transformation. Mapping hides structure. Okay. So the correct classification is deterministic but observationally pseudo-random, where your starting point idea fits mathematically. Your starting point are from an observer who does not know A. Each looks like a fresh independent sample. But in reality they are correlated linear structures, so they are not random variables but deterministic samples of a linear subspace in gamma phi 2 to the power of 8. Your sequence is simply an affine line. Okay. So your intuition correct? Okay. They appear random without the rule, they are deterministic with the rule. This is exactly the basis of pseudo-randomness. This is how cryptography hides structure. They are not truly random, they are not statistically independent. The entropy is increased. Okay. The most important insight in your idea, the real value in what you have noticing, is this: a very simple deterministic transformation like XOR with a linear counter can hide strong structural regularities when the underlying rule is unknown. that is the same principle behind encryption, string cipher, pseudorandom, and so on, but your XOR is low complexity, fully reversible, and so on. Final classification, the statement is for mine. The starting point sequence is deterministic and algebraically structured, but under a hidden parameter. Okay. If you want, I can help you formalize this into a proper models using entropy rate, Kolmogorov complexity view. Why is this? Or hidden variable state space formulation. That's where anyway. Okay, that's where your idea actually connects to you. Okay, let's just okay, sure. This will be just for the record. I will copy paste all this conversation. Also, let me ask it again about Markov, like the DTMC thing. So yeah. Hopefully we don't lose the conversation. Okay. So these are some functions. I'm not on the best mood to read those now. Well, it sounds interesting. Okay. Final abstraction. Oh, it did represented in Markov interpretation as well. Nice. Okay. Final abstraction. This is your paper level formulation. You can define division, hide a fine XOR system. No, don't say it. This is very naive. A process is a hidden fine XOR system with a hidden parameter A. Okay. Very strong formulation. Okay. A model for apparent randomness from hidden linear it's not really important because this idea is discussed before in pseudo-random number generators, but like let's just tell it to, can we formalize it in discrete time Markov chain? Great. Yes, but only if we are precisely about what is random and not state the key point structure. Okay. What else can we do today? Yeah, I think this is enough for today. Can we just select all and then paste it in a Word document? That would be nice. Nice. So now we have all answers in this Word document. Get responses tailored to you. Where did it begin from? Okay. So we don't need this. I have noticed patterns as a result. Okay. This is okay. This is the first thread. So this is really just for, maybe we can like use this to ingest a new chat thread with this conversation and maybe validate topics. Yeah, let's just save this. Maybe we can start a new conversation with Gemini. Interesting. Validate applications of validate applications of XOR patterns from this conversation. And let's also yeah, so my computer is running out of RAM. Okay. Okay. So it didn't paste all the text. It's too long. It's too long for one message. Let's also attach this screenshot. Okay. I cannot upload an image. Okay. So it stopped at this. So it stopped here. Okay. Let's just send this. I'm lazy to refine my prompt. It didn't work either. Okay, let's try again. It won't work. It won't work. Something went wrong. Okay. It's too long for it. It's too long for it. Let's just delete some of the text. Oh, it did work. Okay. Can we just attach the screenshot, please? It didn't work. Let's try again. Okay. Let's ask ChatGPT to, okay, can you or summarize this, the whole conversation on XOR patterns? Let's just say compress this whole conversation. To be able to ingest it in Gemini's context. Can we make this even shorter? So yeah, I think my mic just died, and I'm switched back to my laptop's mic. So, anyways, that concludes the stream today. Again, I wasn't expecting anything useful from those patterns, but we were just brainstorming ideas, uh, and yeah, we we came into new concepts that we couldn't have searched for if we didn't uh, tinker with this with those patterns. So yeah, I will leave it here and see you in the next stream. Peace.